Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. And in today's paper, we're going to talk about hot forging. Hot forging that's been around since about 8000 BC, according to these authors. And yet we are still coming up with new ways to improve and better understand and to modify that process. And the way that they're going to do it here is through graph neural networks for predicting the deformation pathways specifically. This work comes to us from lead author Sam St. John, as well as co-authors there at the University of Tennessee and the Ohio State University. This comes from the NSF Hammer ERC. Okay, in the introduction, the authors talk a lot about the importance of hot forging and how it's evolved over time. They talk about incremental hot forging, where instead of trying to bend it in a single go, it's now multiple strikes that are giving it the desired shape, and how trying to plan for those multiple strikes requires some computational tools that have been developing over time. They point out here that machinists consider finite element analysis to be really the gold standard for this, and there's been some dedicated tools that have been developed. ANSYS, Abacus, Deform 3D, etc., right? But as good as these things are, they are slow, right? It points out here that they can be measured in minutes or hours per operation. So coming up with a plan for how you should deform this thing using these techniques is still too slow, which is why obviously there's a lot of interest in things like reduced order models. There's been many of those. They have a little mini lit review in this paper following this section, and you can read about those. But it also says here that graph neural networks have not been as fully explored as some of the other reduced order models. And they point out here, we intend to prove that GNNs demonstrate learning in a proof of concept experiment with a limited number of samples and a stepwise geometry prediction. So they show their background of all the different reduced order models for predicting this incremental deformation, and then ultimately come to their point where they basically say, like, here's what hasn't been done, right? There's a gap in demonstrating the viability of three-dimensional shape prediction using GNNs in the forging domain. So they're not trying to predict like a single 2D slice of the material. They're trying to predict the full 3D surface mesh, right? That's what they're going to try and demonstrate here in this paper. Now, how do they do it? Okay, so they are going to use a couple different tools. First off, they have data which they took from Deform 3D. Now, they only have, I think, 9 different simulations here, so it is a limited data set. This is really, it's more akin to a proof of concept as I see this than a final product. This is definitely something that's going to be further developed. But that's what they work with now, is this sort of limited initial data set. When you have these things, you have to create a hexahedral mesh, and they talk about how they go about doing that. It says here that they converted hexahedral FEA meshes into connected triangular surface meshes. They then computed node features like velocity and edge distances. And finally, they were able to build a GNN inspired by the mesh graph nets. So if you look here in table 1, this shows you the type of information in the tensor descriptors present in either nodes or edges. They describe what it is and how it's calculated. And then here in figure 1, you have this simplified GNN mesh sort of workflow. It's showing you how they are able to encode and then do message passing and then decoding of the structure operating directly on the mesh. If you look at the types of sort of RMSEs that they were able to extract from these, they were pretty good, in the 6 to 10% range. So okay, looking at the learning curves, this is showing you how the models train over time as you go increasing the epochs of training. And you see generally that they are all able to consistently decrease their loss, so they're able to learn efficiently across these 9 different simulations. The RMSEs for these things got low. They got down to between 6 and 10%. And then critically, they were able to drop their prediction time from 5 to 10 minutes per FEA run to just seconds, right? That is the whole point of doing this reduced order model. That's a big deal. And then, of course, there's this figure 5, which shows you the ground truth versus the prediction step comparison as a sort of visual gut check of how good these things are actually working. So what are some of my takeaways from this? First off, it is still a proof of concept, but it's an enticing one. It's one that makes sense, right? You're taking 2 techniques that both rely on meshes, finite element and graph neural networks, and you're essentially combining those in a really practical way. This could open the door to lots of really cool things, right? You could have reinforcement learning for strike planning. You could have real-time digital twins. Clearly, we are now going to have surrogate models for manufacturing optimization. And the takeaway here is that graph neural networks are going to be a powerful tool in dramatically accelerating the prediction in hot forging, and that's a big deal for advanced manufacturing. Okay, you can read all about it in the latest issue of IMMI.